Welcome everybody to the third section of this course, where we are going to talk about our first unusual neural network, the autoencoder. So in this section we are going to take a look at what an autoencoder is and how you can build one with Tensorflow, the practical application of using an autoencoder to denoise your data, for example, what a dropout layer can do for you, and how this helps you build a neural network that is good at denoising data, but also helps if you have a lot of data and want it to be better on the test set. And in the final video I'm going to talk about what a variational autoencoder is, and how you can use this to generate new images of characters, in this case of MNIST characters. First, let's talk about encoding MNIST characters. We are going to take a look at what an autoencoder is, how you can use several dense layers stacked together to encode and decode MNIST characters, and what loss functions you can use. First, autoencoders. An autoencoder is an unsupervised way of representing the same information with less variables. Now this sounds pretty abstract, but it's kind of a neural way of compressing your data. And if you take a look at the image on the right here on the screen, that's an autoencoder where all the striped lines here are the so one block of striped lines is like one set of neural network weights. So you see that as input to this autoencoder you have a certain amount of numbers, like the 700 something numbers you need to represent one MNIST character. You put them through a neural network to a smaller hidden layer. You put them through another neural network to a even smaller hidden layer, which is called the latent layer. And you try to build two extra layers, one that gets back to a slightly bigger representation, and then another neural network that makes it the same representation as your input. And now what you try to teach your neural network is to keep the input and the output the same. So in this image you see this X and this X with a thing behind it. These two should be the same. We try to make a neural network that has the same input as well as the same output. And this code in the center, the latent variable, the latent layer, can be used, for example, as input for other machine learning algorithms. So this is something that's really good if you have a lot of data, but the data is not labeled. And if you have this, you can maybe find a way to get the same input, like the same representation, but in a smaller amount of variables, so that you need less data points to learn this data set. So this is something to do with beating the curse of dimensionality. The more inputs you have, the more difficult it is to generalize over all the data that you have. But an autoencoder can also be used to generate new images, which we will do in the last video of this section. And you can also use it to remove noise in the input, which we will discuss in the next video. So let's start with autoencoding MNIST characters. And there are multiple ways of encoding and decoding. You can have several ways of encoding layers and decoding layers, like convolutional layers or simply dense layers. And we will start with a simple dense layer approach on MNIST characters. So let's dive into a Jupyter notebook. What I did is I removed all the data in the graphs folder so that our tensor board starts empty again. So you see that no dashboards are active for the current data set. This might be smart to do because otherwise you might confuse the loss of one neural network with the loss of another neural network. And open this Jupyter notebook so that you have the same information in front of me as me. Now you are already familiar with the MNIST characters. We used them in the previous course, we used them in the first two sections of this video. So by now I hope that you know how to make a digit recognition system. So I'm going to go very quickly through all the imports that we need. The fact that we use matplotlib shouldn't be a surprise anymore. And loading all our data in datasets is also something that you're already used to. Now, one thing that might be important later is the input dimension. So we take the first character of the training images and we ask how big it is. So that should be 700 something. Let's take a look if that's still correct. So 784. And we save that to the variable input in. So let's first start with the encoding layer, the encoder. In the encoder, I simply use two dense layers, and I feed the data in my input placeholder. So my input placeholder will contain the MNIST characters, and I get it through a encoding layer, a dense layer, and then another dense layer. And this gives us the latest encoded variable. And so far, it looks pretty much like a neural network designed to recognize digits. But now that we have this with a latent mirror size with 10 variables in center, we are ready to start decoding this information. So instead of that we have this 10 variables in center and now apply a loss function to determine if it predicted correctly what character it is, we start building a decoding layer. So I already built the first decode step. We take the latent encoded tensor and we add another neural network layer that puts this into the same size as the slightly smaller dimension that we had at first. And now it's ready, time to add the last layer, where we can say that the result of the decoder is another dense layer. And we feed this tensor here, first decoded layer. And as output of this dense layer, we want the same amount of information as our input. So that is what we saved in input dim. Input dim. As activation, I will use the sigmoid function, because I know that the input consists of variables between 0 and 1. So by using a sigmoid, we get this nice back. We restrict the variables to be between 0 and 1. Now what I forgot was to run this part of the code. I think that's a smart and sane thing to do. Otherwise we miss the first part of a neural network. And now we got our decoded layer, our result of the decoder. Now to evaluate the performance of the autoencoder, we want the input information to be the same as the result of the decoder, or actually the other way around. We want the result of the decoder to be the same as the input information. Now you, of course, immediately think about, we can use the mean squared error. So we can take the mean squared error between the input placeholder and the result of our decoder. So I already put this here. And you can do this, and this works fine. You can also use the cross entropy loss, which is a bit more harsh, tends to try to get the inputs more towards this ones and zeros. So I added the reconstruction loss here as well, the cross entropy loss. And just try to toy around, try to find what mean squared error loss works better. And I use the Atom optimizer again to minimize the reconstruction loss. Okay, so I want to add some things to TensorBoard because I think it's interesting to see the reconstruction loss, and I will also log the input image and the result of the decoder. I reshaped this as well, and I will show so we can see how well our encoder decoder is working, how it learns over time to represent the characters in a good way. And now training is simple. You just get a lot of input and output characters and we train our neural network. Alright, so our neural network is now trained, and let's take a look at TensorBoard. So we see that our reconstruction loss goes down, so that's great. And when I just wanted to click on the graph, I discovered that I didn't name any of the dense layers. So what I did is I went back to my Jupyter notebook and I added some names just to make it easier to understand what's happening in TensorBoard. What I also did is I added the tf.variable scope to the cross-entropy loss, because otherwise you get way too many tensors interacting with each other, which is pretty unclear. So now our graph looks pretty good. I already removed the gradient. And you can see that we got our input placeholder, we feed it through the encoding layer, and eventually we only have a tensor left that is your batch size times 10. So we encode every image in only 10 values. And then it goes through the decoder. So that's great. Let's take a look at the images that are generated. And this is after 1,000 steps. So we let this run for 1,000 iterations. And you can see that it's already quite well. This 8 is decoded back into something that looks like an 8. This 1 is decoded back into something that looks like a 1. And this 9 is decoded back into something that looks like a 9. But if you go back in time, so let's take a look at the first, or the step 225, you can see that a 4 was very blurry. So over time, the decoded layer becomes less blurry, less blurry, less blurry. So that's great. You can see that our network is really learning something and that you really need this amount of steps. And yeah, so this one isn't the one here. It's just blur. This 8 is still very blurry. I think it's really cool that with only 10 hidden neurons, so we can represent our whole 780 something input neurons into only 10 hidden neurons, and we can just reconstruct the images that came from it, which is cool. Which, yeah, I'm pretty impressed by that. What we did was we encoded and decoded MNIST characters, and we were able to represent 784 inputs. We could turn those into 10 values, and these could be turned back into like the full 784 values. So we really were able to compress this data into a small amount of data. We discussed 2 loss functions, and you used one, but feel free to use the other one and try to compare the differences in decoded values. And we logged our progress to TensorBoard. So that's it for this video.